For billions of years, the moon has stood as a silent sentinel in the night sky, watching over Earth as it spins through time. Its surface, battered and scarred by countless meteor impacts, is an enduring testament to the tumultuous history of our solar system. The moon is not merely a passive observer, but a crucial player in the story of the cosmos. It holds within its dusty, desolate surface a deep history that has been preserved in ways that other celestial bodies, like Earth, cannot. Its lack of atmosphere has kept it relatively unchanged, serving as an archive for cosmic events and solar system processes. In the early days of modern astronomy, theories about the moon range from the fantastical to the highly speculative. Some astronomers suggested the moon harbored vast seas or even life. Yet, when the first spacecraft ventured to the moon and when astronauts landed there, the reality was far different from what early theorists had imagined. Apollo missions in the 1960s and 1970s, which brought back soil and rock samples, revealed a world that appeared devoid of any liquid water. With no rivers, lakes, or seas, the moon's surface seemed to fit the expectations of a dry, airless world. The data collected from these samples led scientists to conclude that the moon was an arid body, a barren rock left to drift through space. This perspective held firm for decades. But, as we now know, the moon's apparent dryness was merely a facade, a surface-level illusion hiding the secrets within. In the early 21st century, space exploration entered a new era with increasingly sophisticated robotic missions. As technology evolved, scientists developed better instruments capable of detecting even the faintest traces of water. These advanced missions, focusing on more detailed and nuanced measurements, began to reveal new and surprising findings. In 2008, India's Chandrayaan-1 mission, carrying NASA's moon mineralogy mapper, M-3, made an astonishing discovery. The instrument detected spectral signatures corresponding to hydroxyl, OH, and water molecules, H2O, on the lunar surface. This discovery was groundbreaking. It suggested that water, or at least its components, existed on the moon, not in the form of rivers or lakes, but locked within the soil and minerals. NASA's follow-up missions, like the Lunar Reconnaissance Orbiter, LRO, and the Lunar Crater Observation and Sensing Satellite, LCROSS, provided additional evidence. By scanning the moon's poles with highly sensitive instruments, these missions identified substantial amounts of water ice in permanently shadowed regions, areas that are never exposed to sunlight, creating an environment cold enough for water to remain frozen for billions of years. The discovery of water in these permanently shadowed regions, especially near the moon's poles, has been one of the most significant findings in modern lunar science. These areas, which never see sunlight, have temperatures so frigid that water ice can remain stable for eons. Scientists call these areas cold traps, and they are among the coldest places in the entire solar system, with temperatures plunging to a bone-chilling minus 250 degrees Celsius. Water in these cold traps, protected from the heat of the sun, has remained in a pristine, unaltered state since the early days of the moon's history. Radar data collected from NASA's LRO revealed high reflectivity signatures in these shadowed regions, suggesting the presence of water ice beneath the surface. Some of the most promising locations include the Shackleton crater near the South Pole. The evidence is overwhelming. The moon's poles may contain vast deposits of water ice, concentrated in these hidden, frozen traps. Understanding the nature of these ice deposits has profound implications. The water could serve as a resource for future lunar settlers, offering not just water to drink, but also a potential source of oxygen and hydrogen for rocket fuel. It could support human habitats, enabling long-term missions on the moon. But there's more. The ice deposits could be part of a much larger system of lunar water that's been cycling through the moon's surface for billions of years. While the cold traps are a major source of interest, the moon's surface itself is also an active, though subtle, producer of water. The solar wind, a constant stream of charged particles emitted by the sun, bombards the moon's airless surface. These particles, rich in hydrogen, interact with the lunar regolith, the dust and rock covering the moon's surface, to produce hydroxyl OH groups. Under certain conditions, these hydroxyl groups bond with oxygen, forming water molecules. This process, called solar wind implantation, is a slow but continuous phenomenon. Over the course of millions and billions of years, the moon has accumulated water at a pace that is difficult to measure with the naked eye, but when examined closely, it's clear that the surface of the moon is, in fact, much wetter than previously believed. Even though the amount of water generated in this way is relatively small, it still provides key insight into the moon's water cycle. The amount of water present depends on factors like the moon's exposure to solar winds, the composition of the regolith, and the overall solar activity at any given time. As we learn more about this process, we can begin to better understand how water molecules might be distributed across the lunar surface and how they could be extracted for use by future explorers. The newfound water on the moon has ignited a renewed interest in lunar exploration. The moon's water ice, once considered an impossibility, is now a key component in future space exploration plans. As humanity looks beyond Earth and toward deep space, the moon could serve as a launch pad for missions to Mars and other distant destinations. NASA's Artemis program is one of the most ambitious efforts in recent history to return humans to the moon. The program focuses on landing astronauts at the moon's south pole, where water ice deposits are abundant. The goal is not just to visit the moon, but to establish a sustainable presence. The idea is to utilize the water, extracting it for drinking, oxygen, and even rocket fuel. This in situ resource utilization, ISRU, could eliminate the need to transport these essentials from Earth, making long-term lunar missions far more feasible. The Viper, Volatile's Investigating Polar Exploration Rover, mission, though recently canceled, was designed to explore these polar regions, specifically to identify and analyze water ice. By studying the characteristics of these water deposits, scientists would have been able to determine the best ways to extract, store, and use the ice. Key knowledge for building a future lunar base. Other nations and private companies are also eyeing the moon's water. The European Space Agency, ESA, is planning missions to drill and analyze the moon's surface to learn more about the distribution of water ice. China's Chang'e program has made significant strides with robotic landers and rovers, with future missions aiming to explore the moon's poles for water and other valuable resources. Meanwhile, private companies such as SpaceX and Blue Origin are developing technologies to transport equipment and resources to the moon. These companies envision not only landing humans on the moon, but also developing the infrastructure to mine lunar resources, including water ice, for future exploration. The moon has become a focal point of not just national space programs, but also international cooperation. The growing interest in lunar exploration has led to collaborations between space agencies across the world. The United States, European Union, China, Russia, India, and Japan are all contributing to the effort to return humans to the moon and utilize its resources. ESA's Prospect mission, for example, will carry out a detailed analysis of the Moon's surface to identify and quantify water ice in the polar regions. This mission will provide critical data for planning future lunar bases and resource extraction operations. International partnerships, such as those between NASA and the Canadian Space Agency, CSA, for the development of new lunar technology, underscore the Moon's role as a unifying project for humanity in the quest for space exploration. As the Moon becomes an active arena for resource extraction, there are important discussions on how to manage and regulate these activities. In the coming decades, there may be legal frameworks established to manage lunar resources, ensuring that the Moon remains accessible to all nations and that exploitation does not negatively impact future generations.